So first we had Oumuamua, then we had Borisov, and now we have 3I Atlas, yet another interstellar body flying through our solar system. And let me tell you, this is a very unique object. And in this video, I'm going to talk about some of the anomalies that make 3I Atlas so very interesting and why it's so important as amateur astronomers for us to try and image it. And with that, I'm going to share some techniques that I'm using, including some free plugins in Stellarium to track the trajectory of this comet, and then how I intend to image it using my C11 SCT telescope in December. So if you're into this topic, you're into astronomy, all things astrophotography, go ahead and subscribe. You're going to love this video and you're going to love this channel. With that, let's jump into 3I Atlas.
So if you follow my channel, you know I've captured comets before, most recently C2023A3, and then I did a video on Comet Kushida, and those were, for me, rewarding projects, but they were also relatively straightforward compared to 3I Atlas. 3I Atlas will be much more challenging, and that's what makes this an exciting project. This is not your average comet hunt. Now, what is 3I Atlas? Well, officially it is designated C2025N1 and was discovered in July of 2025 by the Atlas Survey in Chile. It's only the third confirmed interstellar object ever detected, and that's after Oumuamua, which was in 2017, and Borisov, which was in 2019. Like those other discoveries, 3I Atlas follows a hyperbolic orbit, meaning it's not bound, its orbit, its trajectory is not bound to our sun. It's just passing through our solar system, and that's not to say that the sun's gravity won't affect its trajectory going forward, but it simply means it's not bound to the sun. And but what makes 3I Atlas so fascinating is that it is exhibiting some very unusual attributes. First, it is probably the oldest comet, and it is the fastest body ever recorded moving through our solar system. It's moving at roughly 210,000 kilometers per hour, or 58 kilometers per second. And that's for you F1, Formula F1 or NASCAR racers, that's 131,000 miles per hour, or 36 miles per second. And it's going to speed up as well due to gravity and outgassing activity as it approaches perihelion in October. That would be the closest approach to our sun. Now, about this acceleration, Atlas exhibited non-gravitational motion very early on, as if something was actually nudging it along. Now, likely this was jets of gas being vented off the nucleus. However, it exhibited this behavior at a relatively distant position from the sun, which led to lots of speculation that it could be a form of propulsion, natural or engineered, that we've never seen before. Adding to the speculation is this concept of a targeted trajectory, in that 3I Atlas is following a retrograde path, which means it's moving opposite to the direction of the planets, yet its orbit is lined up with the ecliptic plane. And that's that, think of it as an imaginary sheet where all the planets are circling the sun. And this is coming in at just 5 degrees off of that ecliptic, and the odds of that happening by chance are about 1 in 500. What's even more remarkable, that it's the timing of its pass by is such that it's going to come close to Mars, Venus, and Jupiter. And the coincidence of that happening is about 1 in 20,000. And all of this happens while the comet is hidden behind the sun from Earth's point of view. And to some, these alignments and timings are just rare cosmic coincidences, but to others, they have sparked speculation about whether or not 3I Atlas's path might be not entirely natural. And now there are some other physical anomalies about 3I Atlas, starting with its coma, which is unusually rich in carbon dioxide and less so in water vapor. And that suggests that either it formed in a very, very cold outer region of its parent star system where CO2 ice was stable, or it has a chemistry that's very different from most solar system comets. Now, also, early analysis has showed that 3I Atlas is nickel rich, but it's also iron poor. And that's really strange because most bodies we know carry plenty of iron, and we generally see a mix of iron and nickel together. Instead, Atlas seems to favor nickel, which hints at a very different kind of stellar nursery, or perhaps some kind of catastrophic breakup of an original body. But what makes this even more intriguing is that the iron-free nickel alloys are rarely found in nature. They're most often the result of deliberate engineering, at least here on Earth. And while this doesn't prove anything about Atlas, it certainly raises questions and fuels speculation about whether its composition is natural or something more unusual. Now that brings us to another fact, some of its other physical properties. It has an extreme negative polarization, and that means that 3I Atlas is very unique in that it's reflecting sunlight differently than any comet that we've studied. Normally, a comet will show small negative polarization, about -1 to -2%. Which gradually flips back to a positive polarization somewhere within, let's call it 20 degrees. Atlas, by contrast, is dipping all the way to -2.7% polarization, and it's flipping much earlier at just 17 degrees, which is a sharp, unusual signature that we've never seen before. The easiest way to kind of picture this is that if you were to look at the sun glare off of a body of water, like let's say a lake, usually that glare shifts gradually as you change your viewing angle. But Atlas, its glare is flipping very suddenly and much more strongly, and that tells us that its surface and perhaps it's the surrounding dust may be structured in a way we've never seen before, and it's scattering sunlight in a completely different pattern. Now, is that some kind of stealth technology or a natural phenomenon we just never observed before? Who's to say? But it's a very interesting topic nonetheless. And finally, unlike the other two interstellar objects we've seen, Oumuamua and Borisov, Atlas is considered to be pretty large, with its nucleus estimated somewhere between 3 to 5 kilometers across. And at one point, folks speculated that this thing might be as big as 47 kilometers across. We're pretty sure it's something in the 3 to 5 kilometer range at this point, but regardless, current estimations make it the biggest interstellar visitor we've ever observed, and its sheer size is actually in our favor because it's going to improve our chances, to kind of detect more about it and study its activity in greater detail. Each of these quirks makes 3I Atlas not just another smudge in the sky, but really this is a messenger from a completely different solar system, and it has an amazing story to tell. For professionals, this is probably a once-in-a-generation opportunity to study the physics and the chemistry of a body that was born from another star. And for us as amateurs, amateurs like me, this is just thrilling, to be able to participate in this by imaging this object. And I'm really looking forward to the opportunity to put my telescope on this object and to capture some images. So with that, I'm going to shift now into how to use some tools to make this a little bit easier for you. And we'll talk about how I plan to image this object in December. So the first thing you'll want to do is go to stellarium.org. and download the latest version of the software, which is at the time of this recording 25.2. You'll have options for various operating systems of your machine. I'm on a Windows machine, and I won't go through the installation process because it's relatively straightforward. Just note that Stellarium, it's a free open source planetarium for your computer, and it shows realistic sky in 3D, just like what you would see with the naked eye, binoculars or telescope, but it has a lot of power to it. So go ahead, get it downloaded if you haven't already done so. Okay, once you have installed and you launch Stellarium, you'll see you'll see a representation of the sky, and there's lots of things that you can do, by the way. But we're not going to cover all the features of Stellarium. You'll have to get familiar with it on your own. But what we'll certainly do is I'll show you how to manage plugins. So on the left-hand side of Stellarium, the lower left, if you hover your mouse on the edge, you'll notice that there are options. One of the options is a little wrench icon, which is a configuration window. Now, we can use the configuration dialog to choose plugins. You can do scripts, you can do tools, there are all sorts of things here, but we're interested in plugins. Particularly, we're interested in plugins for the solar system. And there are other plugins, obviously, satellites, remote sync, remote control, but we're interested in the solar system editor. And when we choose configure, we're going to have the option to import elements in MPC format. And we're interested in comets. We can also concentrate on asteroids, but we're interested in comets. And there we can download a list of objects from the internet, and there are a variety of sources that are supported natively by Stellarium. And you can choose from these sources, but I'm going to suggest that we go with the Minor Planet Center orbital database for comets. And with that, we're going to get the orbital elements that are within that. And we can add all new, or we can add new and update existing objects, and we can select which ones. In this case, I'm going to just concentrate on 3i Atlas, and we see it's here. And we're going to add the objects. And now that that is done, I'm going to close the configuration. And you're going to see that in the left-hand window here, I can go ahead and search, and I can type in 3i Atlas. And now I'm going to search for it. And naturally, it is visible at this time, which is in daylight, so it's not very useful to us. But if I zoom in on this, eventually we see 3i Atlas, okay? And we'll talk more about how to track it now, including how to set up your field of view, but it is as simple as that. Now that 3i Atlas is imported into Stellarium from the Minor Planet Center, you're able to treat it like any other object and track it like any other object in the sky. Okay, so you're going to want to set up a field of view in Stellarium, but to do that, you need to decide upon the rig that you intend to use when capturing this comet. Now, I have already stated I'm using my C11 XLT SCT telescope for this purpose, and I've opted to pair it with my ASI1600MM Pro camera, which has about 3.8 micron pixel dimension. Now, together, this combination gives me a focal length of 2800 and an aperture of around 280 millimeters, which means I'm shooting at the native f10 focal ratio. I've chosen this because this is going to yield about a half a degree by a third of a degree of field of view, and we'll take a look now inside Stellarium what it'll look like when we're imaging in December. Okay, so let's get the field of view set up for our rig. And you should have Stellarium open, and on the left-hand side, you're going to see an option for sky and viewing options. So if you select that, and we're going to go to markings, there are several options here. We're going to go to markings, and you'll notice that you can create a field of view, and we're going to set up a rectangular field of view that's equivalent to the field of view of the C11 combined with the ASI 2600 Pro. And if you recall, I believe that was 0.48 degrees, and it was 0.32, I think was the other one. 0.32. Okay. And with that, we now have our field of view set to essentially what we'll be capturing on the sensor. We can close this out, and I'm going to, frankly, I'm just going to search on a simple object here right now, just to show you. So let's say we were looking for M92. And there it is. And if we were to zoom in on that, this shows you how M92 would be framed on the sensor. Okay, but we are not interested in M92. We're interested in 3i Atlas, which now you can always just search for with the search utility. A couple of words about the view here. This is obviously oriented north, and you can see the zenith. You can see our celestial North Pole, and you'll notice that from east running to the west is our ecliptic, and I'm just showing the alt-azimuth lines that give us an idea of the horizon. Each of those green lines represents about 10 degrees above the horizon in terms of view. Now, date and time, I have this set for December for a number of reasons. One, Atlas is not going to be visible in the night sky at midnight, which is when I want to begin imaging, until probably mid-December, and I'll demonstrate that here. Note that on the 1st of December, it's not visible. As I increment day by day, you'll notice that the moon is rising roughly, it's going to be around the 12th that it rises, which so happens to coincide with the appearance of Atlas at the horizon. So right there on the 12th, there, and if we go by hour, we'll see that there's the moon and there's Atlas. This is a terrible time to image. The Atlas will be too low in the horizon and the moon will be too close to it. But if we advance by the day, now we see the moon on the 14th is pretty far separated from Atlas, and Atlas gets to about 7 degrees above the horizon. Then on the 16th, it's probably around 12 degrees above the horizon, and for a nice period of time, 3 hours, let's say, it will be pretty well situated above the horizon, and I'll have ample time to image in total darkness, without any moonshine. So the 16th, which happens to be my mom's birthday, looks like a really good time to do this. Now let's prove that. Let's go ahead and let's search for 3i Atlas, and it will center it on the field of view for us, and you'll barely see that red kind of pulsating marker, and that's where 3i Atlas is. Now we're going to zoom all the way in, and there's our field of view determined by our focal length and our sensor. And I'm actually going to choose a couple of stars. I'm going to try and take center the stars, and when I image, I will be actually imaging the star, or at least that's what we'll be tracking against. And if we notice 3i Atlas is in the kind of bottom left, I'm not sure I like that position because it's going to be on the edge of the sensor, so I'll probably adjust that in a moment. But let's just get a feel for 3i Atlas's travel across this field of view 1 hour at a time. So 1 hour at a time you see Atlas kind of moving around and making its way through our field of view. Now there are different settings that you can impose in Stellarium. I just changed to equatorial mode, and that just changes how Stellarium will basically fixate on the object. It'll simulate a GEM mount, an equatorial mount. Now, again, I'm not sure I like Atlas in that position. I'm going to try a couple different stars as my center point, and I'm going to reset to midnight, and I'm going to run a 3-hour kind of loop through here. So now Atlas is kind of looks like it's running through the frame in a way that I think might be more interesting. It's closer to the center of the field of view. And that could be very interesting. Now, what we'll do is we're going to actually simulate this thing running, a little more quickly. You can from any point in time, you can accelerate what's going on, and you can see now 3i Atlas is starting to move across the screen. I'm doing this because I'm wondering what the impact of 30-second versus 1-minute exposures will be. How much of a trailing effect am I going to get on 3i Atlas? Remember, this thing is really small, and clearly, I think I have a 0.28 pixel resolution, much more resolved than the seeing conditions. So this is going to light up a single pixel, and just watching it minute by minute, gives me a sense of, look at how it's traveling against the star field. That's really what matters here, because what we will ultimately see if we stack a lot of these images, we'll see a streak through the star field. I'm going to wind up stacking individual sections of this and kind of create an animation, but still, over a course a period of a couple of hours, we get a pretty decent amount of movement. In fact, if we were to kind of reset this to to midnight, and let's see, every hour it seems to be moving, I don't know, what are we looking at here? It's moving about, let's call it 2 arc minutes per hour, and at 30-second exposures, that's about 1 arc second of motion. So at 30-second exposures, I would have a drift of just under 4 pixels for the comet. All right, that is a possibility. At 60 seconds, we're closer to 8 pixels of drift, and what the object here is to minimize the drift if we can. Now, so if I center on this Gaia DR3 and then that long number, that's the star that I'm centered on, and simulate 3 hours, it looks like Atlas is kind of going through this triangle of stars, right? You see how it goes right through those 3 stars, and I think that's a pretty interesting composition. So I'm going to wind up, assuming there's no change in course, I'm going to probably wind up centering on this star here, the 8272, and I'm going to watch and film Atlas go right through that and 6012. So let's take a look and see what happens here. Yeah, that's going to look really nice over a 3-hour period, and so that's roughly what I'm going to shoot for at this point in time. Now, remember, the trajectory of Atlas is changing, and so we don't know right now. This is what we think it will be, and this is what I'm hoping that I'll be able to grab. Now, if it changes, obviously we'll revisit this framing, but roughly this is how I intend to image Atlas.
So there you have it. That's 3i Atlas, what makes it so unique, how you can track it with Stellarium, and how you can go about imaging it in December. And if you're interested in my journey with this object, then go ahead and subscribe. I think that this is a rare opportunity for amateur astronomers to share with each other a very unique experience. And with that, I will see everybody on the next video.